Welcome to Let's Talk Micro. Welcome to another episode of Let's Talk Micro. As always, I hope you had a great week. And remember, you can always find Let's Talk Micro on any podcast platform, and on social media. You can find me on Instagram, Twitter, TikTok, and YouTube. On Twitter, Let's Talk Micro One. The other platforms as Let's Talk Micro. Any questions, any feedback, you can always send me an email at letstalkmicro@outlook.com. So I've been saying, in previous episodes, as I'm talking, to stay tuned. Good things are coming your way. And today it's one of those days. I'm very excited about this. About this episode and future ones. So today with me, she's been a guest before in this episode, and the future ones, she's gonna be co-hosting with me. So you listen to her in many episodes. She's a medical science liaison. Her name is Dr. Andrea Prinzi. And I am Luis Plaza, your host. Dr. Prinzi, welcome to Let's Talk Micro.
Hi, Louise. I'm so excited about our new little adventure together. I think this is going to be fun.
I completely agree. Yes, welcome. It's always great having you, and now doing this series, which I'm going to be telling the listeners in a minute. But so this is going to be, for you listeners out there, this is going to be a sub series. So normally, I publish every week. So every now and then, you're going to get an episode, and this is going to be a sub series about antimicrobial resistance, or AMR. In the spirit of Let's Talk Micro, we're really going to be breaking it down. We'll talk about AMR, we'll break down the antibiotics, we'll talk about resistance mechanisms, and more. So, Andrea, where did this idea come from?
Louise, as we were working through some previous episodes, we talked about offline a little bit about how important discussions around antimicrobial resistance are. And we talked about this during the breakpoints episode and the biofilm episode. And it's such a big issue in the world today. But we talked a lot about how clinical laboratory scientists often find this topic to be really, really challenging, right? Like I know when I learned clinical micro, and then when I was training medical laboratory scientists later in my career, antimicrobial susceptibility testing and AMR was by far the hardest topic for folks to grasp. I think a lot of that has to do with, we learn a lot about testing methodologies, but we don't always learn a lot about the drugs themselves, how they're used clinically, when a clinician may choose to use one drug over another, and then resistance mechanisms. We learned some of them, but they're getting really, really complicated. It's getting really complex. And so I think that doing this sub-series is going to be a really awesome way to take a deep dive on antimicrobial resistance, all the mechanisms they're in, things about drugs, drug classes, for the medical laboratory scientist. But of course, for anyone in the clinical community that wants to listen, I think the idea would be to just really get in there, deep dive on these topics, and just make more sense, for all of us. And I think, Luis, you had mentioned too that I don't know if you've had any of these struggles yourself. You're a laboratory scientist. Have you felt that this is a challenging topic for you in your work?
Yes, indeed, definitely, it definitely is, and yeah, we have talked about this, and it's something, it's one of the points of having Let's Talk Micro. It's about sometimes, it's there's so much information, you're trying to grasp everything, learn everything, and then just so with this, I hope to make things easier for everyone. You have it in a nice, neat little place where you can listen to it as many times. So that's what, one of the things that led me to this, because of, yeah, in my career, I work in small labs, large labs. It is a lot of information, and maybe you might have less volume, less organisms, but you still have to know this. And then you start thinking that when you are, as a medical lab scientist, you go through school, and then, it's 2 years, but in addition to micro, you're doing other subjects too. And you're doing clinicals, and maybe you spend 3 or 4 weeks there. So from the get-go, you're barely touching on it. So that's the first thing, right? So you come out of a med tech program, and you come out understanding, yeah, you have a good grasp of your major players. Let's say, your major gram positive and your gram negative. But when it comes to, susceptibilities, yeah, you start learning on the job. And then you maybe train 3 or 4 weeks and then you get signed off. It's very typical in the lab like this. And that doesn't mean you know everything. I mean, it just means that you can get through your work, in a comfortable manner, just without making any mistakes. You can, work on your own, but still, it is a topic. And then, yeah, so you're sitting there, and then when things, there are many things, and then I have encountered this, right? The first day off the bench, you're alone, and then you start getting these flags. Okay, what do I do? It's always nice, right? When the susceptibilities cross over, everything is good to go. But then, let's say when your Vitek is flagging something, okay, what do I do? What is this mechanism? There are so many, drugs classes, when you call MDR, okay, how many classes? What's this class? And that's without touching about the behind, why, how does the drug work? It's a lot of information, and it just takes a long time and a lot of repetition for you to get comfortable with it.
Yeah, and I think I don't know, as we work through these episodes, I think having some of maybe our guests be, clinical, clinicians in the field that have a clinical perspective, that's always really helpful too. I think it helps you tie together what you're doing in the lab with how it impacts a patient when you've got the clinician's point of view, especially on something like AMR or, various antimicrobials and how they work, things like that. So I'm really excited. I hope it'll be helpful. And I think that the clinical laboratory is changing a lot. We see the roles of microbiologists are shaping up to be a bit different than maybe before. And so I think there's a expectation for microbiologists to have some of this knowledge and be able to have a conversation with clinicians and, do a lot of this more complex AST type stuff in the lab. So hopefully it'll be helpful.
Yeah, I agree with you. It's definitely, yeah, it's gonna be helpful, and I hope the audience likes it, and it just, yeah, ultimately all these things that you learn, they're gonna make you better at your job. It's one of those things. So, and as microbiologists, we're in a position where, in the clinical microbiology, especially, we're in a position where we're definitely the result, the information we're putting out there, it's affecting our patients. So it's definitely great to get educated and learn it, and definitely to learn also from the aspect, what happens beyond with the results that we put out there. How do they get interpreted from the pharmacy point of view, from the physician's point of view. So I'm very excited, and definitely. So what I think what we're going to be doing is, like I mentioned on the intro, we're going to be doing, it's going to be sporadically, maybe every month or month-ish, depending. And I'll let the audience know ahead of time. So it's going to be an AMR sub-series. And then, so today we're going to do an overview. And then on subsequent episodes, we're going to start by working the classes of antibiotics. So you, the audience, can understand, what's the class, how do they work, mechanism of action. So that is the plan. And then we're going to have some guests that are from different areas, like from pharmacy. So they're going to bring more information and shedding more light on this. Okay, so Andrea, let's go ahead and for the audience, can you give some background statistics?
Yeah, I think when we talk about something this complex, I think Louise, I love to talk about history, right? So history of microbiology. I think it's really important to understand where we've come from and how we got to where we are today. And the story of antimicrobial resistance is very interesting and kind of fun. It's really loaded with all sorts of funny little elements. And so I'm just going to talk about the story of how essentially penicillin came to be, but then touch on development of other antimicrobials, how resistance kind of came into the picture, and then a little bit more about where we are now. I think some folks are probably familiar with the story of Alexander Fleming, but I will just start there. So Dr. Alexander Fleming, back in the day, we're talking like 40s earlier here, where he was working on cultures of Staphylococcus aureus in his laboratory. He'd been growing up these cultures, studying the bug. A lot of people were dying from infections with staph at the time. And he decided to go on vacation and left his plates with his lab assistant at the time came back from vacation and found that some of his plates had been contaminated with a fungus. And everywhere this mold was growing on the plate, the bacteria would not grow. So there was kind of this zone of inhibition around this mold. And he thought, wow, this is interesting. It seems like something in this mold is killing the bacteria. And so he really was the one that discovered penicillin because it came from Penicillium mold. You don't hear a lot about the story of what happened after that. He was the first one to make this hypothesis and start investigating it, but he actually had a really hard time purifying penicillin from the mold. And so at the time he was calling it mold juice. He was trying to extract it and use it and demonstrate that it really worked, but he was having a really hard time demonstrating that it was working the way he thought it was, and he essentially gave up. And so a little further down the road, there were two individuals named Howard Florey and Ernst Chain who found Fleming's research and assembled a team of scientists to work solely on what they called the penicillin project. And so they extracted enough of this compound or penicillin to start animal trials, and they were able to infect mice with streptococcus bacteria. And I think there were 8 in total. 4 that were given penicillin survived, and the 4 that were not given penicillin died. And they said, wow, this looks like this really, really works. And so they put this group of women to work known as the penicillin girls, which, if this is not a movie, there probably should be one. I want to know more about them. They were employed to tend to fermenting broth and basically farm a few precious milligrams of penicillin from this broth every week. So at this point, they're just getting very little out of the mold that they're growing. They're getting very little penicillin. And so more and more work starts to happen with this. People are trying to figure out how to make this a more efficient process. They come up with the Department of Agriculture in Peoria, Illinois, comes up with some new fermentation methods, new techniques that help purify penicillin a little more efficiently. And, this is working, but it's still not that fast. And then very serendipitously, they put out a call for like a global mold search. So they're looking for a mold or penicillin or penicillium mold that will produce more penicillin than what they'd gotten so far. And soil samples were sent in from all over the place. Nothing was really taking off until a woman named Mary Hunt, who was an assistant at the Peoria lab, found a rotting cantaloupe at a market, and it had penicillium on it. And they played with this mold and found that it produced 6 times more penicillin than Fleming's original strain. And so they were able to start getting more penicillin out of this new batch and ferment this a little more readily. And actually, US pharmaceutical companies were not that excited about committing to large-scale penicillin production. And it was actually World War II that really created this demand for penicillin. I think they realized that more folks were probably dying from infection in the field than they were combat. And if they didn't do something to help fight off infection, they were probably going to lose a lot of soldiers and potentially lose the war. So that really created some skyrocketing interest in the development of penicillin. And so the U.S. made sure they had sufficient penicillin stocks to satisfy the demands of the armed forces in the U.S. as well as their allies throughout the war. So I think that that's a very interesting start. That's the background story on penicillin, but I would say it's important to note sulfonamide actually came first. I don't know, I couldn't tell you exactly how much time or how many years or months before the discovery of penicillin, but sulfonamide was first, and resistance developed to that fairly quickly. And then we also saw resistance to penicillin develop very quickly as well. In fact, I think there was resistance documented before penicillin ever was on the market for clinical use. And that's a really important point because I think sometimes people don't realize that resistance or antibiotic resistance occurs naturally in these organisms, especially if the antimicrobials or the antibiotics that are being produced are coming from nature. So like from a mold, for example, we see organisms developing resistance mechanisms in nature all the time. We really just help speed it up with excessive antimicrobial use. And so this is what we saw with penicillin resistance. It was immediately pretty much that there was resistance to the original penicillin. And then methicillin was developed, or the second group of beta lactamase resistant beta lactams were developed to try to avoid this resistance mechanism that had been developed against penicillin. And that lasted for a little while, but then Staphylococcus got smart again and developed additional mutations and things. And that led to what we know now as methicillin-resistant Staphylococcus aureus, which is typically due to mutation in the penicillin binding protein 2. So these things just happen very quickly, developed pretty quickly over time. And I think that it's a good example of how readily the organisms can make these changes. We've seen an explosion of resistance mechanisms in other organisms over a pretty short amount of time. For example, the methicillin resistance that we see in Staph aureus is when an organism's acquired the MEK-A gene, which encodes for the penicillin binding protein 2A, which enables the bacteria to sustain cell wall synthesis when other PBPs are inhibited by beta-lactam antibiotics. So basically, when a beta-lactam comes in and tries to hook to a penicillin binding protein, it can no longer do that if those binding proteins have been modified. And so the organism can continue to maintain its cell wall and not basically fall apart. And so we've seen all sorts of different types of mechanisms. We'll get into those later when we talk about additional mechanisms. That's sort of the background, some history on when we first started seeing antibiotics, and then resistance popping up not long after they were developed.
I like that story, and definitely I as a graduate student, I study it, and definitely, it's fascinating, and I always, I don't know, and in all these types of stories, I always enjoy learning, right? It's like what sometimes, in those times and the things, all the discoveries, and I don't know, it's always amazing what people do, right, with their intellect and how far, the things that we can achieve. Um, and I remember, yeah, the cantaloupe, and so, but yeah, you mentioned the resistance, and yeah, it's true. As a tech, I definitely see it a lot, and I do remember, I feel like I haven't been in this field that long, like 10 plus years, but I feel like I've seen a lot change. And I do remember before, like you will barely get like a KPC, for example.
Oh, definitely.
And now, we get so many, and then MRSA's like,
Everywhere.
it's like very normal in your cultures, you see it in those wound cultures, most of them are MRSA.
Yeah, that was absolutely the case when I first started in micro MRSA. We were not seeing a lot of it. And we certainly weren't hearing about it as widely distributed in the community as it is now. I mean, it was really more of a hospital pathogen, and we still didn't see it all that often. And when we first started talking about carbapenem resistant organisms, that was like the worst case scenario. We didn't have any, but we were on the lookout for one. It's just crazy, like you said, how quickly things have changed in a period of, like 15-ish years. It's not actually that much time to have things develop so quickly.
Yeah, no, and yeah, I do remember, like you had that one, and it was just, I mean, it was a little bit of a pain when you had to do like the modified Hodge test, and
Oh gosh, yeah.
people in the lab dreaded that, and it's like, oh, do I have it? And then, do that, and like as of right now, I pretty much, I've seen, like Enterobacter cloacae, I've seen Citrobacter, Proteus. So most of the Enterobacterialis, with the KPC, and a lot more, like in all the benches. So it's definitely something that's been on the increase. So as you were telling the story, and you were talking about people dying from infection, this is one of those things that when I was growing up, like I used to like, think, what about like time travel? If I can be at another place in time or seeing these things. And nowadays, like the microbiologist in me thinks that I will probably get very sick if I go back in time and to one of those historic moments, like stay away from the water. My body probably couldn't handle it. So I don't know, just something that came to mind as you were telling the story.
I can't imagine. Well, it's funny. We say this now. We say, like, I can't imagine living back then and not having options. But it's honestly where we're headed if we don't get stuff figured out. I mean, talk about this post-antibiotic era. It's very scary, right? That we might come up across infections that can't be managed by anything we have available to us. It's very, very scary.
Yes, yes it is. And so for your listeners out there, like I said, this is what this are the topics that we'll be talking about. I mean, I don't know if you read, if you heard, but definitely, AMR, it's a global concern. You're seeing resistance. There's a lot of antibiotics, and then that it's been, some not like overused, and then we see this increasing, and sometimes, at some point in time, I would like to eventually, as I go through this journey, to maybe one day get more, because we do get a lot of requests sometimes, even like we don't with minimal amount of organisms, or the organism is very susceptible. And I'm just going to be very quick about this because we're just getting started. But like, for example, like with staphylococcus, sometimes we get a very susceptible profile, and then we get a lot of requests for it. So that's on a side note. But definitely thank you for the background, Andrea. So what's the current state now?
So, like I said, it's interesting because things continue to change, and I think some of the differences between where we were and where we are really striking. So, like you mentioned, and like we were talking about MRSA not really being all that prevalent, not really that long ago. Now, what used to be only a hospital pathogen is now pretty much equally distributed between the community and hospital settings. You see people colonized with MRSA all the time. Like you're saying, wound infections are often infected with MRSA. It's really just all over the place. So we're seeing a lot of that kind of movement. We're seeing a lot happening in the gram-negative rods. It's pretty wild, very, very hard to keep up with. The first plasmid-mediated beta-lactamase ever described in a gram-negative, so meaning a mobile genetic element that could be transferred between organisms. I think of it as like a baton in a relay race. I don't know if that's accurate or appropriate at all, but I just think of like a little bacteria like handing a baton to another one, and that's your plasmid. It's just very easy to transfer these resistance, the genetic information for these resistance mechanisms. But the first one that was ever described was from an E. coli isolated from the blood of a Greek patient named Timonera, I don't know if I'm saying that right, in the 1960s. And it was called the TEM1 enzyme. And so for a while, that was the one that we really saw spreading. It was plasmid mediated. We hadn't really been seeing this kind of thing before. And so it quickly spread across the globe, and it's been identified in other gram-negative organisms. But then not long after that, we saw the appearance of an extended spectrum beta-lactamase mechanism called CTXM. This enzyme's called CTXM. And so now this one is the most dominant across the world. So just another shift where, we start with TEM1 and then CTXM sort of takes over. And the prevalence of these enzymes will definitely differ between geographic location, but I just think it's interesting to see how these things continue to move around the world and what becomes more prevalent over other things. We've also got, a lot of carbapenemase activity popping up, more so than, like you said, we saw even just a small amount of years ago. And I guess the main take-home message from this overview episode is that lots and lots of different mechanisms out there, and hopefully we'll go through all of them, but very little development of new antibiotics in the pipeline. And so that's one of the scarier things, is we're seeing a lot of resistance popping up, seeing a lot of change in epidemiology over time with respect to resistance mechanisms, but not a lot of aggressive antibiotic development. And there's a lot of reasons for that. It's pretty complicated, a lot that goes into it, but that is a bit scary. And so I think if you look at the literature, there's lots of great literature out there right now on the state of AMR. I think one of my favorites most recently was the paper published in the Lancet in January of 2022. I've mentioned this before in previous episodes, and I'm sure folks are fairly familiar with this publication now. I think this is a very, very popular one. It was written by individuals on the Antimicrobial Resistance Collaborators Group. And they estimated deaths and disability adjusted life years attributable to and associated with bacterial AMR for like 23 different pathogens and 88 pathogen drug combinations in over 204 countries and territories in 2019. So it's this really comprehensive look at very big data, trying to just get a grasp on how urgent this AMR crisis is and how many people are potentially dying from infections associated with or directly related to antimicrobial resistance. And they concluded that they estimated that there's about 4.95 million deaths associated with bacterial AMR in 2019, including 1.27 million that were directly attributable to bacterial AMR. So a major problem is causing a lot of deaths, particularly in lower middle income countries, and is really a big problem.
Yeah, indeed it is. And touching back a little bit on what you said, yeah, I think I remember when I was going through like an AMR class that yeah, it's just like I think it's like over maybe like in 50 years or something like that that a new class of antibiotics hasn't been made. I mean, we come up with more stuff, but it tends to be like, it's more combinations, like like a beta-lactamase inhibitor combination and things like that, but like a brand new drug. And yeah, and like you said, just many reasons out there. We're not gonna really get into that today. Just today's just the overview. Um,
That's a good point, though, Louise. I would just add one more thing in there. I think that it's scary that we don't have a lot of development of antibiotics, but I think the good thing about that is that it's encouraged us to look outside of just antimicrobial development and think about the other ways we might be able to slow down the progression of AMR. So that's why there's so much emphasis on like the One Health approach right now. So thinking about how we use antibiotics in animals and agriculture, farming, water quality, things like that, and how organisms spread between people. Because if we can prevent the spread of infection, then obviously that's a good thing. But it's a good thing not only because you reduce the risk of death and morbidity, but you also reduce the risk of someone acquiring an organism that could become drug resistant and then passing it on to someone else. So thinking more about like infection prevention and control and how antibiotics are getting used not only in humans, but in every other component of life, essentially, the food that we eat, the places we live, that's all become really, really important and pressing, I think, front of mind for all of us right now.
yeah, and that brought to mind about with sometimes with the overuse of antibiotics. That I think I spoke to this to a guest before, but I do remember like me growing up in Puerto Rico. Like I do remember like everyone knew someone that always had access to antibiotics. And it's like, you start feeling something, oh, just take, penicillin, and I'll take this. And then, you start feeling better, you stop, and that's it. Yeah. And people don't realize, what you're doing when you're doing that, but it's a very common practice.
That's such a good point. There's a ton of literature on this as well, the unrestricted use of antibiotics in other countries, right? Like where there's perhaps maybe not a stewardship structure, or it's just really easy to get your hands on things. And maybe we do an episode on that too, because there's a lot of cultural components that go into that as well, right? Um, and lack of infrastructure or resources for various things that may lead to that behavior. But it's a huge problem, the unrestricted use of some of these antibiotics elsewhere.
Yeah, yeah, it is. And sometimes, it made me, as I got older, and it's just, it made me cringe a little bit. And it's like, oh, you're not feeling well. Oh, don't worry. I'll talk to the pharmacist and I'll get you some. No, I don't want that. So just, yeah. So definitely, yeah, it's scary. Um, so, we're bringing light into this, for and telling the audience. So as far as, what's being done.
I probably got ahead of myself a little bit when I started soapboxing a few minutes ago, but there's a lot of global effort happening right now dedicated towards trying to slow down AMR. It's a lot of it's focused on the things I've already mentioned. So things like infection prevention and control. These would include both community-based efforts, particularly in lower middle income countries. Some of those, Louise, have to do with behavior change around prescribing, unrestricted prescribing. In some of those areas, it's really challenging because there's limited access to diagnostic testing. And so they mentioned that in the Lancet paper, that there's not infrastructure for diagnostic testing that can confirm, what's causing an infection. And so sometimes things are just given, just to treat the patient because they're very ill, but they don't really know what they're treating. Although there's a lot of work, I think a lot of people might argue that it's not enough. Some of the tasks that are being worked on are perhaps maybe a little easier to tackle than others. So, maybe getting in there and working on prescribing in another country is challenging, but making sure everyone has access to clean water feels almost impossible sometimes. And things like that are really important. As long as there's no access to clean water in some areas, this will persistently be a problem. And so some of the approaches are actually very public health focused and very, very, very challenging, but really top initiatives that should probably be addressed, but are very, very hard to address. Also thinking about, there's a lot of organizations working on and thinking about preventing infections through the use of vaccination. So this is important because I think, maybe vaccination doesn't seem like it's directly related to AMR when you first think about it, but it absolutely is. We think a lot about patients that get maybe a secondary bacterial pneumonia because they got influenza. And then that pneumonia is caused by a drug-resistant organism where they get antibiotics for that, and it encourages the development of drug resistance. Or in general, getting sick and then having, a suppressed maybe immune system and acquiring other infections, or even just getting infections with things like Streptococcus pneumoniae, which there is a vaccine for. And actually, there's a lot of deaths globally were associated with Streptococcus pneumoniae in that Lancet study. So, using vaccines when we have them for organisms that could potentially become resistant to antimicrobials, or, potentially preventing viral illness that could either exacerbate or lead to secondary bacterial infections that may get antibiotics directed towards them. Those things are all really, really important. Thinking about reducing exposure to antibiotics unrelated to treating human disease. So like I said, in farming, in all of our food, antimicrobial stewardship in the hospital setting, which I think particularly in the US, we've gotten quite good at in a lot of places, but where the challenge really exists, I think now, is thinking about reducing antimicrobial use or bringing it back a little bit in the outpatient setting. So perhaps you have more resources to really make this a success in the hospital setting, where you've got the patient is in-house, you've got contact with them pretty consistently, you've got a team of hopefully educated and informed individuals working on stewardship initiatives. Whereas out in the community, it's a whole nother ball game, right? You've got people coming into urgent cares, people wanting antibiotics for viral illness because they just want to feel better and they think that's going to help. Challenges around behavior and communication, and then losing track of a patient and not knowing if they're going to come back or if you're going to see them again. What does the follow-up look like? Those things are really, really challenging. And then finally, a lot of groups working on investment in the antibiotic pipeline, although we do know that this, like we said, is pretty slow. That might also involve improving access to second-line antibiotics in locations without widespread access. So there's discussion around, if there's an area that maybe doesn't have access to the best drug, can they get access to second-line antibiotics? It doesn't have to be either the best case scenario or the worst case scenario. Or there are alternative options that might help slow down the development of resistance that include using something like a second line agent. But ultimately, everything should be approached with a One Health approach, which I think is really coming around. People are really starting to handle AMR work in this way. And then I guess the final thing that I'm seeing a lot of is creative uses of big data for things like AMR surveillance, or understanding epidemiology and trends over time, so that we can try to get ahead of some of these things and maybe guide therapy more appropriately, or try to prevent spread and detect these things a bit earlier, so we can prevent any acquisition of nasty resistant bugs.
Yeah, indeed, and definitely very important, to have some, yeah, some communication between all these parts, and yeah, and education, which is, it's very important. You mentioned, as you were talking about what's being done, and you mentioned, the clean water that sometimes, sometimes I maybe here, we don't think about much. Here in the United States, it's, we don't have any issues, but that's not the same for other parts of the world. And you mentioned, with the antibiotics, and that's something that I never thought about it before. And now, with the podcast and listening to more people and stuff, yeah, I heard all the, let's say all the drugs that we have here that we have access to, it's not the same from other countries. And, they definitely, are working with less. So it makes it challenging.
It does. And I think we should always try to keep equity in mind when we talk about things like this. We have access to a lot of things here, and we are fortunate in that way, although we do have our own challenges, associated with antimicrobial resistance, especially since we are big users of drugs and, antimicrobial therapies and the healthcare system as a whole and tools. We use these things a lot. I think that it's always important to have in mind the ways the world, globally, how people of the world contribute to the problem of AMR, and how to think about directing resources towards fighting it, right? It's that idea again of no one place being completely immune to disaster. We saw this with COVID-19. We will see this again with any other pandemic that comes our way. Is that just because something is happening outside of your country doesn't mean it won't eventually get here. And so trying to mitigate AMR related challenges in other countries is a good thing to do for global health, including our own country here in the United States. So, making sure folks are vaccinated, making sure there's access to antimicrobials, that may be a better option. I can't tell you how many times I've been in a conversation with a colleague who's elsewhere in the world, and I'm just, I'll say something about like, oh, well, did they switch to this antibiotic? And they're like, we don't even have that here. That's not even an option here. I'm just so used to, saying, oh, we've got XYZ, we should switch to XYZ antibiotic. But like you said, I mean, that may not even be available in other places. So just thinking a lot about how to lessen the risk of development of AMR everywhere is really important.
I agree. We're definitely, the world, it's definitely very connected now. And like we say, we saw it with COVID, and it just, with all the travel, and so it's just, things can spread quickly. So yeah, it's definitely a global concern. Do you have anything else, Andrea?
No, I think that's a good intro.
Right? Yeah, I think we hit the main points, and
Yeah. Sounds a little disastrous, I think, but everything's going to be okay. We're going to work through this together, everybody.
yeah, yeah, definitely. So, for you, the audience, just, I hope you enjoy this, and definitely listen to it. Always, if you have any questions, any feedback, I mentioned social media, the email. But like I mentioned before, I think one of the best things that we can start doing is going over the different classes. So I was thinking, Andrea, what about, let's say, shall we do the beta lactams?
Yeah, let's do it. I think that's a great place to start. Probably the most popular, right? Who
Yes.
knows?
Yeah. Well, sounds like a plan. So stay tuned.
Can't wait.
And that, my dear audience, it's the end of this episode. I hope you enjoy this upcoming AMR series for antimicrobial resistance. As always, I enjoy bringing this information with you. So this will be between our regular episodes, but this is very important material that we need to know for our jobs. And in the spirit of Let's Talk Micro, we are just making it simple, so really breaking it down so you can learn at your pace. And I am so happy that Dr. Andrea Prinzi is joining me on this journey. I am excited, and I think you should be as well. I am really excited about finally breaking down this material. So please Continue bringing that passion to what you do. It's so important. We do such great work. So, as always, stay motivated, stay safe, and of course,
Continue talking micro.
continue talking micro. Until the next time. Bye.